As you can see from this diagram, light spans a broad range of both frequencies and corresponding wavelengths. Of this broad range, the part of light, or the range of light that is visible, that can be seen by human eyes, is quite narrow, spanning from 400 nanometers to 700 nanometers roughly in wavelength. In this diagram, you can see how there are regions where the wavelength is short and the frequency is high, and then on the other hand where the wavelength is very long and the frequency is low. And you can see how the spectrum of light is split up into different ranges. Besides visible light, at even shorter wavelengths, we have ultraviolet, and then X-rays, and then gamma rays. And you can see that these regions overlap somewhat. The ranges aren't really super well defined. Different sources will give you different cutoffs, and you can see that also they overlap a little bit. For longer wavelengths than are visible for humans, we have infrared waves, and then microwaves, TV, FM bands, and that they fall in the radio wave part of the spectrum. And then there are very just long wavelengths. So all of these wavelengths and all of these frequencies obey the wave equation for light, which we remember is frequency times wavelength equals velocity. And since we're talking about light, the velocity is c, the speed of light. Now, as light travels, we use the ray approximation or ray diagrams to show how light is moving. So typically light will travel in a roughly straight line until it encounters some sort of boundary between materials. So to draw a ray approximation diagram, you would draw straight lines in the direction of the light travel, and we call these rays. The wave fronts are surfaces perpendicular to these rays that show where the wave of light would have the same amplitude and phase. Now, there's an important concept when we're talking about light and light traveling, which is the index of refraction. So the index of refraction is defined as being the speed of light in a vacuum, c, divided by the speed of light in a material. Now, I can hear you thinking, wait a minute, isn't the speed of light, the speed of light, c, always? Well, yes and no. The speed of light is always the same if light is traveling in a vacuum. When light is traveling through a material, it still travels at the speed of light between atoms, but it interacts with the atoms along the way. So as light travels through a material, it will get captured by an atom, the atom will get excited, and then it will spit it back out and the light will continue on its way. So the light stops to interact with the atoms in a material, and as a result, overall, on average, its speed gets slowed down just a little bit. So the index of refraction is a number that's always bigger than 1, and the bigger the index of refraction, the more light slows down because it's interacting with the atoms in the material. So the index of refraction of air is very close to 1, which is the index of refraction of a vacuum. So the index of refraction of air is 1.000293. So it's still very, very close to 1. The index of refraction of something like water is higher. It's about 1.33. Now, the frequency of light doesn't change as light passes from one material into another. So say you have light going from air into water, the frequency does not change. So we know that the velocity of light in a material is equal to the frequency times the wavelength for both materials. And so if we look at the ratio of the wavelengths, we can rearrange these expressions and see that the wavelength is the velocity in a material divided by the frequency, but we know the frequency is always the same, and so we can rewrite this velocity as being equal to the speed of light divided by the index of refraction. There we're just rearranging this equation, n equals c over v, for v, and inserting that in. So since the speed of light, c is a constant, those cancel. And when we do a bit of algebra just to simplify this expression, we'll find that lambda 1 times n1 is equal to lambda 2 times n2. What this is saying is that the wavelength of light in a material times the index of refraction of that material is equal to the wavelength of light in another material times the index of refraction in that material. So the frequency doesn't change as light passes from one material into another, but the wavelength does. So let's say medium 1, so material 1 is a vacuum. If that is the case, then the index of refraction for vacuum is 1, and we're going to call the wavelength in a vacuum lambda naught. So that's just the wavelength in a vacuum. And so if we put that into this expression, we have the wavelength in a vacuum times 1, the index of refraction of a vacuum, is equal to the wavelength in some other material times its index of refraction. So rearranging this, we can see that another way of defining the index of refraction or finding the index of refraction is that it's equal to the wavelength in a vacuum divided by the wavelength in that particular material. So next, let's consider this question. As light travels from a vacuum to a medium such as glass, where the index of refraction is greater than 1, which of the following remains the same?